It is our last section of the course, 7.3. What are we going to talk about? We're going to find maxima and minima for multivariable functions. Very exciting. Good way to end, kind of tying it back into a concept we did previous in the course with one variable functions, right? So a little bit of an introduction before we get into what would a local maximum or local minimum be when you've got multivariable. Let's just talk about the graphs so we can identify. Let's get familiar with these. Probably haven't worked with these much before. So typically we write the function as z equals f of xy. Kind of like, you see what we're used to is y equals f of x, that sort of thing. Same idea. Now x and y are both independent variables. Z is the dependent variable. Depends on both x and y. And because we have three variables, x, y, and z, our graphs are going to be three-dimensional, as I've noted there. So let's look at an example of just graphing a point. What would a point look like in 3D? So I've got an example here, and I'll just go ahead and show you the whole example right now. Let's plot the ordered triple 2, 3, 5. And of course the 2, the 3, and the 5 are the values of x, y, and z. Can we just plot a point in 3D? So here's how it's typically depicted. We have an x-axis, a y-axis, and a z-axis. Usually the way people draw it, the x-axis is like coming towards us out of the page, like so, as you draw it kind of at an angle. The y-axis runs horizontally like that, and the z-axis, so the x and the y are perpendicular, and the z-axis comes perpendicular to both of them straight up the page like so. Now I'm only showing the positive x, positive y, and positive z axes, but there is a negative x axis if we kept trailing back this way, the negative y axis that way, the negative z. Okay, but that tends to clutter things up, so not unusual to just graph the positives to keep it simple for now. Okay, so let's try and plot this point, 2, 3, 5. So how would we do that? Well, starting at the origin, let's walk out 2 units on the x-axis. Then we're going to move 3 units on the y from there. So this location is the point 2, 3 if we thought of just the xy plane. From there we need to go up 5 units. So I've gone up 5 units on the z, but you notice this is at sort of an angle, so these would line up vertically. If we were to drop down eye level, these would be at the same. So we went up 5 units, but we stop right there. So hovering right there in space is that point, that ordered triple 2, 3, 5. Okay. Let me show you what would a local max and a local min look like. So I didn't draw the x, y, z axes just because, again, I didn't want to clutter things up. But if we're talking about 3D, a local max, it's not just going to be, in 2 dimensions, it's just like the top of a curve, like a hill. But in 3D, we've got a 3-dimensional version of a hill. So it's kind of this bump. And of course, the local max is right up there at the top. Local min, same idea. I've almost got like a cone or something upside down. It's rounded off. So it's this valley down there at the very bottom, of this cup or whatever it is. And so again, 3-dimensional minimum. It turns out there is one other type of extrema when we go to 3 dimensions. Let me show it to you and then explain why we have this sort of thing. So it's called a saddle point, and they're not the easiest thing to draw. So I did my best here. We get the name saddle point because literally the shape looks like a saddle that you would, climb up into on a horse or something. So what's going on? So in this direction, it's dropping down. So that point is a minimum in this direction. But if we thought of the graph from the other, perpendicular to that from this other direction, it's a maximum. So it's almost like, imagine, it reminds me of like throwing a blanket. If you threw a blanket on like a clothesline or something, like it would dip in the middle, but then the blanket is falling off in either direction. Right at the middle there, that's the saddle point. Again, like why this third combination? So if you think of the maximum, if we look in either direction, so if we thought of like maybe this as the y and this as the x. Sorry, my camera's kind of trying to focus over and over again. So as we look in the y direction, that's at a peak in the y direction. And if we were to look in the x direction, it's also at a peak. So it's maximized in both the x and the y. The min is minimized in both x and y. So if we thought of it coming, this way, that tangent line and that tangent line in 3D, then okay, so in this direction it's minimized, but then also in this other perpendicular direction, it's minimized. So it's a local min. The saddle point is the combination. So one of them is at a min, but the other is at a max. And so, now we have three combinations of the ways we can get like a horizontal tangent line, really. Okay. So there are the pictures. How would we actually, what's the procedure, to find these points? Well, let's define a critical point. Okay. A critical point, we used to think of the critical point as just an x value. Now we're going to think of it as an xy point, so an ordered pair. And so hence the name critical point versus like critical number or something, because now we do have an ordered pair. Okay, so it's the xy point AB such that both the first partial derivatives equal 0 at that point. So if you remember the original critical number, it's where the derivative equaled 0 or does not exist. We're not going to consider the does not exist when it comes to multivariable. We're just going to consider where things equal 0, which makes it a little bit easier on us too. Okay, so that point will cause the partial derivative with respect to x to equal 0, and the same values of x and y will cause the partial derivative with respect to y, cause that equal to 0. Both of them have to happen, okay? So what do you do with that? Then we can apply this. We call it the multivariable second derivative test. Okay, so there are a series of steps for the multivariable second derivative test, and this is obviously going to help us identify is that point AB, once we know it's critical, is that point a local max, is it a local min, or is it a saddle point? Okay, so step one of this test, well, find all of those critical points AB. Sometimes that's relatively easy to find these critical points. Other times a bit more challenging. So we're going to have a couple of examples later. But okay, obviously first we need to identify our critical points. Number two, we're going to find all of these. Okay. Now comes the second derivative, the second order partial derivatives, we say. We're going to find the second derivative with x, so fxx, and we're going to evaluate it at that point AB. We're going to call that value capital A. Okay. Then we're going to find the second order partial derivative fxy. We're going to evaluate it at the point AB. We're going to call that capital B. And finally, capital C is fyy evaluated at AB. Okay, so we're looking at all these partial derivatives. Truth is, we're really testing the concavity from every angle. You notice that we don't put fyx we only have this one, fxy. Turns out that's all we need to know. So we don't need the fyx when it comes to this, where this is going. Okay, so we find these three values, capital A, capital B, capital C. What do we do with those? Now this seems completely random and out of the blue. I'm not going to explain why this is true, so just go with it. We're going to calculate this value right here. So we got our A or B or C. We're going to find AC minus B squared. Okay, and depending on what the value is, that's going to help us determine, is it a local max, a local min, or a saddle point. There are technically four cases. So take a moment to write these down, but of course I'll talk through each one. If that value, AC minus B squared, is positive, then we'll look to our A value. If A is negative, then that means we've got a local max. Okay, so again, if that value is positive, but our A value back here was negative, we've got a local max. Right. If that value was positive, but when we look back at our A value, it was also positive, then we've got a local min. Where do these come from? Okay, so a positive value here means that the derivatives in the two directions agreed. Okay, so either we've got, either they're both positive, right, like we saw a moment ago, like the local max, right? So both are at a maximum in both directions. And A is negative. So remember, A is a second derivative. If that's negative, that means you're concave down. All right, well, if you're concave down, you've got a local max. Okay, the next one, if that's positive, then that means both your derivatives, well, okay, so again, like we know they agree. We know they're either both positive or both negative with this. But then if A was positive, that means you're concave up, means you've got a local min. And then the saddle point, all right, what if, so these both had AC minus B squared is a positive number. If AC minus B squared was negative, you don't have to go any further. That means that the two did not agree. I'm not going to attempt to draw the saddle point again. You saw it a moment ago. Then that means that the two did not agree. One's positive, one's negative. We don't have to look any further. We know it's a saddle point. There is one last case. If AC minus B squared equals 0, then we say the test is inconclusive. We can't do anything more with that. That's not going to come up in any problems that we see. So it should be noted though, because well, positive, negative, what if it just equals 0? Then we don't know at that point, but that's not going to be an issue for us in this course. Okay. So I think I've set this up pretty well. We'll do an example in the next video.